Welcome students. The topic for the day is data structures. So what are data structures? Generally, a program or an application consists of two components, that is the data part and the algorithms part. Data is the information that would be used by the program, and algorithms are the rules or the instructions that turn that data into something useful. So we can remember two things, that data plus the permissible operations on that data is known as the data structures, or data structures when combined with algorithms form programs. In other words, we can say the data structures are specialized formats for organizing, processing, and retrieving and storing data in a computer systems. The specialized operations that we talked about are in the previous slide are the organization of data, processing of data, retrieving of data, and storing of data, for which the data structures specialize. That is why we say that these are specialized data structures for these operations. They enable data manipulation, retrieval, and management, which is critical for optimizing algorithms and improving performance. So using specialized data structures helps in optimizing algorithms. That means getting full efficiency out of those algorithms if we use data structures, and hence improving performance. So we have different kinds of data structures. The fundamental ones, fundamental types, or the primitive data structures are int, char, float, and dub. You might have already worked with them. These are handled by machine instructions directly. That means they are the most basic data structures, or data types, out of which then the non-primitive data structures would be derived. That is where the discussion of the non-primitive data structures comes. So we have already seen the non-primitive data structures like arrays, linked lists, stacks, and queues. In fact, in the coming slides, we'll be discussing stacks and subsequently queues and linked lists. Arrays, up to now, you might have already gone through the implementation of arrays. So as far as the stack is concerned, it is a derived data structure or the non-primitive data structure, and our this topic will be exclusively dedicated to the working of stack. For the time being, we would move to another of the data structures that is known as nonlinear data structures. So this type of data structures, elements are arranged hierarchically as compared to arrays and linked lists. So examples include trees and graphs. So these are two more data structures we'll be taking up in the subsequent lectures. For the time being, we'll be moving to a stack. So a stack is a linear data structure following the LIFO principle. LIFO means last in, first out. That means in this type of data structures, the elements or the values which would be going into a stack would be coming out last, or the last element or value which would be going into the stack would be coming out first, or displayed first, or removed or traversed first. So examples include, if you stack plates, the last plate that you would put on a stack, that would be the first plate to come out. Similarly, the undo operations in text processing softwares like Word or any other softwares, the last operation would be undone first, followed by others. So here is a diagrammatic representation as to what happens when you insert elements or the values into a stack. So on the left hand side, we have an array in which A, B, and C as values, hypothetical values, have been inserted into a stack which has been implemented here in the form of an array. We would also be seeing in subsequent slides the implementation of stacks, that you can do it in using an array and using a linked list also. So in this example, we are taking the array example, array implementation example. So here in this array, which has been represented or shown as a stack, we have inserted A, B, and C as three values. So you can see the pointer at the top, which is named interestingly as top because it keeps track of the topmost element or value in a stack. So to begin with, top points to nothing, absolutely nothing. Then when you inserted a value like a, top would be pointing to that. Then you inserted b, top would be pointing to that, and at last you inserted c. That means a top would point to that c value. So you can see also there we have mentioned a word push. Push is a special term used for insertion in case of stacks. So when you say you are pushing an element in a stack, it means inserting an element, and it generally happens from the end, from the one end or the top end, and we use the variable top to keep track of as to which element is at the top of the stack. Similarly, on the right hand side of the diagram, you can see the pop operation happening, which means removing elements from a stack. So here in this example, you have removed C. So it means C has been popped out or removed. So you can also see that top has been updated to B. That means once you remove C, now my top element would be B. And if we remove B also, then A would be our topmost element, right? So implementation or representation of or the operations of stack, what operations are permissible on stack are push, as we already discussed. It adds an element at the top. Similarly, you can display or traverse the values in a stack. We call the traversal or the display operation. Pop removes an element from the top, and peek views the top element without removing it. So there is a basic difference between pop and peek, that in case of pop, you remove an element and update the top variable to the next element, while as in case of peek, you only view the topmost element without updating the top pointer. So push operation, what does push operation do? Say we have an array of 5 elements and you want to insert elements into it. You can see here that we have a variable top which points to -1. -1 in case of array or any negative index in case of array means that there are no elements. There are no elements, since in case of array indexing starts with 0. So any negative index, it means an kind of an invalid condition, meaning that there are no elements, since the index represented by the top doesn't fall within the domain of correct indices when representing arrays. So top is equal to -1 means there are no elements. So then we are coming up with a value of 5 and it would be added to the array. Top would be updated to 0. Then we would insert another or push another value, which is 3. 3 would be pushed and top would be updated to 1. Similarly, 6 top would be updated to 2, 4, then 4, top would be updated to 3, and then we would push at last 2, and top would be updated to 4, right? Then if you want to display the same elements of the same stack, so you would be doing that from the top end. That means 2 would be the first one to be displayed, then 4, then 6, and then 3, and then at last 5, right? Similarly, we have another operation called pop. How does that work? We are taking the example of the same array. So here 2 would be popped up. We are using a pop function to pop a value from the top. So 2 would be displayed and top would be updated to 3. That means next element which was subsequent to 2. So top was 4 up until now. So when we popped that 2, top would be updated to 3. Then doing or firing another operation, pop operation onto the same stack, we would be removing 4 and top would be updated to 2. Then firing a peek operation or method onto that stack, it would give us 6. As I discussed already, that 6 would be displayed as it would be pointing to the top without actually updating the point. So top would remain as 2. Say firing another peak operation would again give you 6, and again no updation as far as top is concerned would happen, right? Now coming on to the stack implement. Now on to the implementation part. So we'll be writing a C program for the implementation of stack using arrays. Starting from main function, we have given user a choice of entering 1. In that case, a push function would be called. Then display. If he wants to display the elements of stack, he or she should press 2, 3 for pop, and 4 for peak, and any other key to exit. Now we want an integer answer from him, integer value from him, which will be stored in C. Then we are switching C and checking the cases for that value of C. Case 1 means if user has inputted 1. In that case, C is basically, he or she rather, is wishing to insert or push an element onto stack. In that case, we should ask for a value which is supposed to be pushed onto that stack. Then we'd be calling the push method to carry out the push operation. So we would be going to push function first, checking its code. So here is the push function. So in case of push function, before explaining the push code, let me show you the global declarations first. That we have declared a stack of 30 elements and a top which is equal to -1 at the beginning, and then we have declared a variable n which is supposed to store the total capacity of this stack, which is equal to 30. That means in this example we are putting a limit of 30 elements to the stack. It cannot store values beyond 30. Of course, you can change this to 20 or 40 or some other value. For this example, n is equal to 30. So basically, if you want to concentrate on this line first rather than if condition, so what we are doing is that we are pushing a stack, we are pushing that element which has come here as an argument, that is n. N would be stored in this array which we have named as stk, or the stack. Remember here that we are doing a pre-increment. Since the value of top is -1, it needs to be incremented first. That is why we are doing the pre-increment. Whenever doing pre-increment, it means that increment the variable first and then do the concerned operation. Concerned operation here is to push this n onto the stack, but then we would be first trying to get a valid index. Since it is an invalid index that is currently stored by top, means that there are no elements, since we are coming to this push function for the very first time. So this plus top would increment the value of top to 0 from -1. So this instruction would become stk 0 is equal to n. That means the 0th position of this stack would be holding the value of n. And of course, we in the meantime incremented this top value or updated this top's value to 0. So meaning that the topmost element in the stack is at index 0. So coming to this if condition, since we have put a limit of 30 elements that can be stored by this stack, we would want to make sure that top is well within the limits. n-1 means 29, so top's valid value as far as this operation is concerned, or when this operation should occur, is that top should be at most 28, because we are doing the pre-increment. So in case of 30 elements, the valid indices would be from 0 to 29. So would be well off having our top value below 28. Then we can go to 29. So for the last time, if we are coming here in this function with a value of 28, it would be permissible because plus top plus 28 means 29. So that also is a valid value for the index. But beyond that, the operation shouldn't happen. In that case, it would print an overflow statement, right? So coming back to the this main function, so case 1 means that we have finished pushing elements. Since you are using break, that means the control would now come out of this switch case, but we are still in while loop. So it would go back to while. Since we are using here the infinite loop. Infinite loop means while one means that one here means that the condition has been implicitly or explicitly made true by the user for this loop to run continuously. Then what is the exit condition of this loop? Exit condition is that whenever the user concerned presses any value other than these 3 or 4 values, that means 5, 6, 7 or 11 or 21 or some other value other than 1, 2, 3 and 4, because 1, 2, 3 and 4 have been uh, handled, I should say. In fact, you should add a case 4 here, which we have not done here. So in case of case 4, we should have implemented the peek operation, or it should handle the peek operation. So case 4 means and would peek, and the printed element would be printed, and then would be having a break, right? So suppose since we are going to the while loop again and the condition is true, the menu would come up again, and suppose the user presses 1 again, it would be asking for another number, and we would be again going to push function. So going to push function, it would again check whether we are within limits, and then push the element onto the stack by incrementing the top variable, which was in previous run 0. Now it would be 1. So stk1 would be storing our next value, and the process would go on as long as the user presses 1. So next time, for example, the user instead of 1 enters 2. So in case of 2, we'd be going to display function. So here is a display function. So assume that we have values of 1, 2, 3, 4 and 5 in the stack. That means the topmost element is 5, but top would be pointing to 4. Since the first element would be at 0, next one at 1, next at 2, next at 3, and the last element would be at index 4. So before printing elements, I should make sure that there are elements. So checking if top is equal to -1, as explained already, that top is equal to -1 only at the beginning of this execution of this program, since there would be no elements. So in that case, you should display a message like an underflow. I have printed here. So else means that the top is not equal to -1, or indirectly meaning that there are elements. So top variable, for example, which points to 4 in this example, is being stored in T. We would be using T because T is being updated. If we use top here directly, it would basically update or change the value of top, which we don't want. Say, for example, after carrying out this display operation, we want to again push an element, the 6th element. So we should remember, or we should have the value of top. So if you if you use top directly here, so it would change to some value that would be detrimental to our program execution, as it would be losing the track of which the topmost element was. So we are using a temporary variable t in which top has been stored. Then we say while that t value or the top value is greater or equal to 0. That means we would be printing elements from the top towards the bottom for which the last valid index is 0. In the meantime, we are doing what? Stack t. We are printing stack t. So in this example, as I said, we have the elements of 0, 1, 2, 3, and 4 and 5. So the last index is 4 or the top is 4. So stack 4 would be printed, but while coming out of this instruction, it would be decrementing t. So t would now become 3. Then it would again go to the while loop. 3 is greater or equal to 0? Yes. So it would be printing stack 3 and subsequently t would be updated to 2 and so on. So at last we would be having a value of t as 0. 0 would be equal to 0 if not greater than. So stack 0 would be printed and t would be updated to -1. For which this condition would stand false and the control would come out, right? So this was basically the display operation. Similarly, we have the pop operation here. If user wishes to pop an element, so from the menu he would choose the third option. He would press 3 and for 3 pop function would be called. So what is that pop? As you can guess, we would like to make sure that there are elements, there is no underflow condition. In that case, we would return without any element, obviously. So in case of having elements, as is the case in the current example, say we have 1, 2, 3, 4, and 5 as elements of the stack. So control would go to else and it would return stack top. It would return stack top. What is that? That is topmost element, that is 5. But while coming out, it would be decrementing the top. Also, as discussed in the previous slides, the top should be updated to the next valid index when doing a pop operation. So similarly for peak, even though I have not written it here, you can try it out. So in case of peak, this would be as it is. In case of else, you would be returning stack top without doing this top minus minus, right?